So I'm going to start going forward once the homework grades have been published in GradeScope. That after a few days, then the regrade request will close. As I mentioned before, just a way to keep things moving, and so we don't fog up the TAs with older homework that they have to try and go back and remember what's going on. So homework 3 grades were published this morning. So I'm going to have the regrade request closing on Friday. Right, so take a look, see if there's anything in there that you have concerns about, and try to get those in. Also, homework 1 through 3 are also exported to LMS. So in LMS, the letter grade is calculated as a running total, and it automatically accounts for dropping the lowest 2 homework grades. Right, so if you looked in there before today, you would have noticed that you don't have a letter grade, and that's because there was less than 2 homework assignments. So now that there's 3, you'll start to see an estimate of what your letter grade is. So right now it's just based off of whatever your highest homework grade is. So definitely if you take a look and you see, low B or C's right now, definitely reach out to me so we can have a conversation, see maybe where you're having some difficulties, either making deadlines or maybe with the concept, so we can address that sooner rather than later, right? We don't want to wait till the end of the semester and then not be happy with our grade and try and fix it all at once. So definitely, if you have any concerns as you're looking at that at any point in the semester, please come talk to me so that we can address it as soon as possible. Okay. All right, so today we're going to be talking about Fourier transforms. And so how we're going to get to that is first we're actually going to look at the Fourier series again and see what kind of information we're getting from that representation that we can use to kind of get to this idea of a Fourier transform, right? So when we were looking at our signals up to this point, we're focused on the time domain, right? So we essentially have a value for our signal at each time value, right? But if we go into the frequency domain, it turns out that we can also represent signals by the content at a specific frequency, right? So we can look at the magnitude and the phase, because we end up usually having some kind of complex number when we go into the frequency domain, and we'll kind of see what that looks like. But we want to see how can we actually get to this idea of figuring out what is the frequency content of a time domain signal. So what we're going to do is we're going to go back to one that we've actually seen quite a bit here so far. And this is a periodic pulse train. So we have something like this, where we're going to pretend that I drew that to scale, and this T1 and that T1 are the same length. And this distance here, T over 2 minus T over 2. All right, so we have a periodic pulse is a period of capital T, and we have it centered around 0, the non-zero pulse. And so what we had seen is that if I take this x of t, I can compute the Fourier series, and my Fourier series coefficients ak are 2 sine k omega 0 t1 divided by k omega 0 t, true for k not equal to 0, and 1/2 with k equals 0, with omega 0, 2 pi over t. So if we take a look, and we'll take a look at just the non-zero part here, and if we were to multiply by the period capital T, we'd have this AKT is 2 sine k omega 0 t1 k omega 0. So we could actually think about this as being like sampling this sinc function at intervals which have length omega 0. Right, so the idea here is that I have my sinc function, which kind of looks like a decaying sinusoid. So this is that function there. And what's happening is that each AKT is like I'm taking my K. So I'm sampling at omega 0 when K is 1 with the value T A1. And I can sample at minus omega 0 and I have T A negative 1. And as I increase K, I'm sampling at intervals of omega 0. Okay. So a way that we can interpret this is that our original signal x of t consists of sinusoids and the frequencies are multiples of that fundamental frequency omega 0. All right, so we've kind of alluded to this idea a couple of times as we were driving our Fourier series, right? Because as we were looking at Fourier series being representing using those complex exponentials, which had those frequencies k omega 0, right? So we're getting at that in a slightly different way, right? So instead of looking at those exponentials directly, we're looking at this idea that these AKs are almost like sampling this sinusoid. Okay. So the question is that this seems to work pretty well for this periodic signal, but we don't have a periodic signal. So if a signal is not periodic, then a way that we would interpret that is to get to an aperiodic signal, our period would go to infinity, right? Because that's not periodic. So it would repeat at infinity because it doesn't repeat. Or in other words, your omega 0 goes to 0. Right? So before we get to that, let's take and kind of do an intermediate step here. And let's just say, what if t was doubled? Right? So let's just see what happens if we increase our period a little bit, how that changes our samples. Right, so I have the same signal here, but instead of the original t, I had a higher capital T. Okay. So then, in that case, when I did my sampling, right? So this part here, the thing that I'm sampling is the same, right? So we have the same sinc function here. But what's going to happen is that my samples are going to be closer together. Or, in other words, my x of t consists of more sinusoids. And so why that is since t is double, omega 0 is halved. So our samples are closer together, right? Because when we look at our original samples here, right, so we can see that our interval where our samples are occurring at our omega 0, right? So if we increase t, this omega 0 gets smaller, so these samples are going to get closer together, which means that we're going to have a lot more of them. Okay. So what this implies is as we keep increasing t, we're going to get more and more and more samples until eventually, when we take our t to go to infinity, which is the same as omega 0 going to 0, then what that means is that we're going to have all frequencies represented, right? So for a periodic signal, when we're representing that signal, we only needed to use frequency components, which are multiples of that fundamental frequency, right? So we have omega 0, 2 omega 0, so on and so forth. But once we get to a signal which is not periodic, then it turns out to represent that signal in the frequency domain, we're actually going to need to use all of the frequencies to do that. Okay, so for our Fourier series, when we go back to that, right, so we had AK equals 1 over t, and let's say we go minus t over q, t over q, right? Doesn't matter, we're just going over one period. X of t, e to the minus jk, omega 0 t, dt. Right, so if we looked at it this way, and we looked at our AK t that we looked at before, then we have our t's, x of t, e to the minus jk, omega 0 t, dt. So then in this case, when t goes to infinity, this AKT is like sampling this integral at intervals of length omega 0. Right, so it's the same kind of idea that we looked at with the sinusoid, right? That's kind of like taking these k omega 0 samples that we're taking of this entire integral. And so this idea here is our Fourier transform of x of t. So we're going to use a capital letter, right? So I try and be pretty explicit about that because I know, right, so x's and things like that are kind of hard to tell lowercase versus uppercase. So I tried to really exaggerate my upper versus lower for these types of letters. So if we see an uppercase letter, then that indicates that we're in the frequency domain, right? So things are going to be in terms of this frequency omega. And when you see a lowercase, that's typically going to be the time domain equivalent, right? So like x of t, like you've seen so far. So this Fourier transform is defined to be this integral x of t e to the minus j omega t dt. So really that's the key takeaway from what we've discussed so far is this integral here. So one note on notation, right? So I tend to have a little bit of a shortcut notation. So if we're going from our time domain signal x of t, right? So you see before I have the fs when we're going to Fourier series. When we're doing the Fourier transform, I'm going to use ft, and we'll have x j omega. And depending on what you're looking at, some will drop the j and just say x omega, right? So sometimes they're used pretty interchangeably. Yeah. So because what we're doing is kind of like we're sampling, taking like an infinite number of samples, so kind of that k omega 0 we're taking to omega. And so because your k omega 0 is going to become, your omega 0 is going to 0. So you have so many samples that basically we're representing it as this omega, which has become a continuous value. Whereas our k omega 0, those k's were integers and was discrete. So now we're kind of extending this into a continuous case. Yeah. And so we'll take a look at using this in a little bit. First, we'll take a look at what the inverse transform is like. All right, so again, we're kind of going to get to this idea from our concept of Fourier series. So our inverse Fourier transform so if x of t is t periodic, then we have our x of t we can represent using our Fourier series like so. Right? But one thing that we just arrived is this idea that essentially this Fourier transform, where our omega is this k omega 0, because we have a periodic signal, is the same as this ak t. Or in other words, ak is 1 over t, this Fourier transform. So what this means is that if I want to get back to my x of t from this Fourier transform, what I can do is I can substitute in this AK here. So my x of t is 1 over t x jk omega 0 e to the jk omega 0 t. Right, so I substituted in this new AK into my Fourier series. And if I replace my t with the 2 pi omega 0, I can pull out the 1 over 2 pi, and I get a sum of omega 0 my apologies, I got cut off a little bit. Right, so this would be true for a periodic signal, right? But what we're looking for is the general inverse Fourier transform, which is for aperiodic signals. So that means that we want to take this omega 0 and see what happens as it goes to 0. And it turns out that this summation, as we take this limit here, that this is going to become a Riemann sum. So this actually turns into an integral. So we can say that our x of t, if we're given our Fourier transform, we're going to take an integral to get it back. All right, so maybe not exactly what you were hoping to see. Turns out that in both directions we have a beautiful integral that we get to work with. But hopefully not too bad as we start looking at them. A couple of things that can be easy to trip up the first time, right? So we're going from the time domain to the frequency domain. We have a negative exponential and no coefficient out front. And it turns out when we're going from the frequency domain back to the time domain, we have a positive exponential and an extra 1 over 2 pi factor. So both of these are in your reference tables. So definitely make sure that you look at those, because that's an easy one to, you get one in your head and then just start going with it, and it turns out to be, you know, you have a negative instead of a positive, something like that. It's an easy one to mix up the two of those. Okay. So as I said, we'll look at some examples in a moment. One thing first is that because we have these integrals, and these integrals have this exponential in them as well, there is one thing that we are concerned about, and that turns out to be the convergence of our Fourier transform. So if you're looking at the book, this would be in more detail in section 4.1.2. So if you don't have the book but you're interested in more detail, I can also try to share that information with you as well. But the idea from there is that this integral for our Fourier transform is guaranteed to converge to a finite value if one possibility is that the integral of the absolute value of our signal squared is finite. So this means that the signal is square integrable. Or 2, that the integral of just the absolute value is finite. So the signal is absolutely integrable. Okay. Because definitely if we're trying to figure out a transform, we're going to end up getting a function of omega. And so then think about like Bode plots where you can plot magnitude and phase versus omega, kind of the idea that we're getting at here. And so if you're trying to compute this x omega and the integral to do so doesn't converge, right, then the result doesn't help you at all, right? You have like an infinite value and you can't really do anything with it. And so that's why to know whether or not this Fourier transform exists, we need to see, is this integral actually going to converge to something finite that we can work with? And it turns out that the condition for that to occur is the signal that we're converting to the frequency domain needs to be square integrable or absolutely integrable. And there's also some additional conditions, which I won't really get into, but there's also some continuity conditions. So if you're a math person and you're interested in that, these are the Dirichlet conditions. But the main one that we're interested in for this class that we'll be checking to know whether or not the Fourier transform exists is to check one of these conditions, right? Either the square or the absolute integrability. So let's take a look at an example. So I'm going to take and we want to compute our Fourier transform of x of t, where x of t is 1 between -1 and 1, and 0 otherwise. Right, so our x of t, if we sketch this out, it's just a single pulse. So the first thing that I need to do when I'm asked to compute the Fourier transform is first make sure that I can actually compute the Fourier transform. So to figure that out, the first thing we want to do is see, is x of t square integrable? So the definition of that is we take a look at our integral of x of t absolute value squared dt. Right, so if we look at our signal x of t, it's 0 when we're less than 1, 0 when we're greater than 1. We square it, it's still going to be 0, absolute value, still 0. So we don't have to worry about anything going on outside of -1 to 1. We look at our x of t in that interval, the value is 1, absolute value of 1 is 1, 1 squared is 1, so it turns out that that's just 1. And so I do my integration and I get a finite value. Okay, so since that is finite, I know that my Fourier transform integral is going to converge. So I can actually do the computation. Yes.
The absolute value there, if x is negative, or if x is like complex, how does absolute value work?
So you would take like the absolute value is the magnitude, right? So if you have a plus bj, and you do the square root of a squared plus b squared, that's your absolute value. Okay. So now if I want to compute here my actual Fourier transform, then I need to take the integral of x of t e to the minus j omega t dt. And so once again, I can make the same observation that my x of t is 0 outside of -1 to 1. So I can decrease the bounds of my integral to -1 to 1. In that interval, my x of t is 1. And my exponential here stays the same. And so when I do the integral here, just the integral of an exponential, so I get minus 1 over j omega e to the minus j omega t minus 1 to 1, right? So I definitely recommend that when you're doing your integral, write down what it is that you're substituting, right? Because depending on which way we're going, right, when I'm going from x of t to x omega, all of my t's should disappear and I should only have omegas. When I'm going the other way, all the omegas should disappear and I should only have t's. Right? I've definitely seen people say they're going from omega to t, and then they substitute in all of the t's when they do the integral, right? So definitely it's just a good practice to make that note to yourself. Here's what I integrated over, so that's what I'm substituting in to make sure you have the right result at the end. Okay, so I get a minus 1 over j omega e to the minus j omega minus e to the j omega. I'm going to bring the minus sign in here. So we have e to the j omega minus e to the minus j omega over j omega. If we look at our reference tables, we can recognize that this difference here is the equivalent of 2j sine omega. So we have 2 sine omega over omega, or as we learned, we could also represent this as the sinc function. So our x j omega is going to look something like that. So that case was pretty straightforward. We have a nice square integrable signal, and so we were able to just compute the Fourier transform directly, and everything is fine. So let's take a look at a little bit more complicated of an example. And we want to do the Fourier transform of x of t e to the minus at ut. So what this means is we're going to have our signal is 0 when t is less than 0. And then we're going to have an exponential after t equals 0, right? So one thing that we noticed here is we didn't actually say what a is, right? So the question is this a decaying or growing exponential? And we'll see that depending on the value of a, that's going to impact whether or not the Fourier transform actually exists. Because if we take the case where a is a negative number, okay, so it's less than 0, then we have if we're looking at the square integrability of this signal. Right, so first thing that I can recognize is my u of t here, right? So u of t is going to cancel out everything before 0. So this is the same as the interval 0 to infinity. And then when we take the absolute value of e to the minus at, we're just left with e to the minus at. And then we square that, right? So we're multiplying e to the minus at times itself. So we can add our exponentials to get e to the minus 2at. Okay. And so now when I compute this integral, okay, so when I substitute in t is infinity, okay, so we have e to the minus infinity times a minus number. So our minus numbers are going to cancel out. So we have e to the positive infinity minus e to the 0. E to the positive infinity is infinity. Right? So it turns out that if we have a growing exponential here, that it is not square integrable, right? So it is, our result is not finite, which means that the Fourier transform does not exist for this case, right? Because since this won't converge, if we try and plug this into our Fourier transform integral, it will not converge there either. If, on the other hand, we have a greater than 0, right, so I can go through the same process here. And we can make the same conclusions. All right, so I'm going to skip ahead a little bit. So you have minus 1 over 2a. So in this case, a is a positive number. So we have a positive times a positive with a negative. All right, so we have a negative number times positive infinity. It's going to give us e to the negative infinity. E to the negative infinity is 0. So in that case, it converges to a finite value. All right, so in this case, as long as a is a positive number, then this signal is square integrable. All right, so then if I wanted to compute the Fourier transform of x of t is e to the minus at u of t, where a is greater than 0. Right, so that's a key thing that we learned from checking that square integrable condition. So in that case, I can substitute into my integral. E to the minus AT, U of t, e to the minus j omega t, dt. Once again, I can use my step signal to reduce the bounds on my integral. And then I can combine my exponential terms. So I have e to the minus a plus j omega t dt. So we get minus 1 a plus j omega e to the minus a plus j omega t, evaluated from 0 to infinity. We have minus 1 over a plus j omega. When I substitute in t infinity, so this j omega part is just giving you a like a sine cosine type of oscillation. And so it's really this real part which is determining whether or not that sinusoid is going to be decaying or growing. And so since we have a positive a, then that means that we're going to have a negative infinity here. So we're going to have a decaying exponential. So this is the equivalent of e to the minus infinity. Same thing we saw before. This is 0, that's 1. So our Fourier transform is 1 over a plus j omega. All right, so as you can see, you can have, when you go into the frequency domain, the possibility of complex numbers, right? And that's where that idea of having magnitude and phase, like what you would see in a Bode plot, comes from. So we will mention a few of the Fourier transform properties. I just want to introduce one now because I will use it a little bit. And as I have said, right, some of these you're probably going to get sick of hearing, but it turns out Fourier transform also uses the linearity property, which means that if I have x of t and its Fourier transform is x j omega, then if I scale my time signal, I just need to scale my transform. And if I have a Fourier transform for one signal and the Fourier transform for another signal, then if I combine my time domain signals, my Fourier transform is going to be the combination of those individual Fourier transforms. I said there's lots of properties and we'll talk about more. Just want to introduce that one because we will use that a little bit. All right, so there is one thing though, right? So we said for the Fourier transform to exist, it has to be square integrable, right? So we actually have to kind of have this idea of some kind of finite property of our signal. But if you looked at the reference tables, what you would notice is that there are Fourier transform pairs for signals that don't actually satisfy that case, right? So it turns out that there are some signals that do not satisfy the convergence conditions that we can still have a Fourier transform found using some special tricks. So little things that we can recognize that still allow us to have Fourier transforms for a few special signals that technically don't satisfy the square integrable properties, but yet we can still tweak them knowing some special relationships. So one example of this is if we want to compute the Fourier transform of x of t is the impulse signal delta t, right? So the delta of t does not satisfy the convergence conditions. However, if we look at our x j omega, right? So we can use our definitions that we derived from our derivation of this delta of t, and we can recognize that this delta of t multiplied by this exponential, that we can just take the value of this exponential where the delta of t is non-zero. So we have e to the 0, and we're left with the integral of delta of t. And so we've defined that integral to be 1, right? We know it's 1 because since this is infinite bounds, it definitely includes that impulse. E to the 0 is just 1. So it turns out in this case that even though the convergence properties are not satisfied for delta of t, it turns out that knowing what we do about the delta function, that the Fourier transform, we can actually get a finite value. So we can say that delta of t has Fourier transform of 1. And so we can actually utilize this idea to find the Fourier transform for another type of signal. So we have cosine omega 0 t, right? So we know that this is not square integrable, because if we were to plug that in, right, we're going to take the integral from minus infinity to infinity of this periodic signal that never actually converges to a value, right? So you're going to end up getting an infinite value if you try and do that integration. So we know that it doesn't satisfy the convergence property, right? So this cosine omega 0 t is not square nor absolute integrable. But it turns out that cosine omega 0 t has a Fourier transform which looks like this. Okay. So the question is, does that actually make sense? Why is that the case? Well, if we take a look at the inverse Fourier transform. Okay. So the inverse Fourier transform, we're going to get 1 over 2 pi, the integral of our x omega here, which is pi delta omega minus omega 0 plus pi delta omega plus omega 0 times e to the j omega t d omega. All right, so both of these have a pi, so I can pull that pi out and cancel it out here. And then I'm going to break up this integral into the integral of omega minus omega 0 and the integral of plus omega 0. Okay. So I can use the same trick that I used before, where I can recognize that I'm going to only have the value where this delta is non-zero. So in this case, right, so when it's going to be non-zero is when the argument is 0, or when omega is equal to omega 0. So this term is the same as substituting in omega 0 for omega. And then we're just left with the integral of delta, which is 1. Similarly, over on this side, right, so the non-zero value here is when omega is equal to minus omega 0. So we can substitute that into our exponential, pull this exponential out, we're left with the integral of delta, which is just 1. So we have e to the minus j omega 0 t, which, if we look at our reference tables, is our cosine, right? So it just happens to be that we can see, well, based on the inverse Fourier transform, yeah, we actually do get that signal back. So we can see by the pairing there that this must be my time domain signal and that my frequency domain signal. And it turns out you can do something similar for sine as well. All right, but instead you'll end up getting you'll have negative term in here and also a j term. So we can also extend to some other signals that we're going to encounter a fair amount. Right, so if you have x of t is a constant signal, it turns out that the Fourier transform for this constant is 2 pi delta omega. Right, so we can probably kind of see where this is going, because we kind of look at this idea of what we had for our cosine, right? It's almost like we're taking omega 0 to 0 and getting a constant value, right? So if we look at the inverse Fourier transform here, 1 over 2 pi, we have our integral, substitute in our Fourier transform, then we have e to the j omega t dt d omega, right? Because we're going from frequency to time, so we want to get rid of our frequency. And so these 2 pi's here are going to cancel out. non-zero when omega is equal to 0. So we substitute in e to the 0 is just 1. And we're left with the integral of delta, which is just 1. There's also another example in the book, example 411, if you're interested, where they go through another common signal, which is u of t, where you get 1 over j omega plus pi delta omega, right? So those are some of the common ones that we'll encounter that technically they shouldn't have a Fourier transform, but by recognizing some key things, which we can see mostly revolves around that special impulse signal, we can actually derive a Fourier transform, even though based on our definitions, technically they might not. So just a couple more things, going to show a couple of the properties, and then we'll review those more after the exam. So definitely it'll be a while since Friday will be exam review. We have no class on Tuesday because that's Monday classes. Then we have the exam. So you're probably not going to remember any of this by the time we get to that following Tuesday. So definitely we'll review some of these properties at that time, but kind of give you a little bit of a preview as well of what some of these are. And you can probably guess, because pretty much everything that we've derived, we've kind of went through the same properties, so they tend to be useful. And it turns out, since a lot of these are related to our LTI systems, that they have a lot of similar properties as well. So one of them is time shifting. So if you have a signal x of t and Fourier transform x j omega, then if I shift my time signal, I'm going to get x j omega e to the minus j omega t0. Right? So definitely nice to have these properties so we don't have to keep doing those integrals. Right? Once we have one, then we can utilize this so we don't have to go through that process again. And there's also the time flipping property, which says if x of t has the x j omega Fourier transform, then if I flip the time, I negate the frequency. Kind of flipping in the same way. So I might come back and do a proof for each of those, but I want to make sure that I go through Fourier transform of periodic signals first, if you have some of that on your homework. Yeah.
Will this be on the exam or
No.
So
No.
this is like that exam they did.
Yeah, similar to the back exams, is definitely take a look at the practice exam that was given. And we'll be going through that on Friday. We'll be going through a good portion of that, and then some of that I might post separately so you have a chance to review it before recitation. Since recitation right before the exam, I want you to be able to ask questions. Yeah.
How much is each exam worth? 25% or 20?
So 20, 25, 25, 30. Yeah, so 20 for homework, 25 for exam 1 and 2, and then the final is 30. So Fourier transform of periodic signals. All right, so I've already alluded to with cosine and sine, right? Since they're periodic, they're not square integrable, right? Because we have infinite length signal that doesn't converge, so it's going to, if you take the integral, you're going to get an infinite value. So the question is, what can we actually do to get the Fourier transform for a periodic signal? Right, so our periodic signals are not square absolute integrable. Okay, and so we can recognize that it could be finite over a period, right? But then you have infinitely many periods, so it's always going to be infinite. So what we could do is we can use a trick with our impulse function. Right, so I had said early on when we first introduced the impulse function that we'd see it again and again and again. It tends to be very useful to us. Well, so here's yet another case where we can utilize that. So let's first take a look at the Fourier transform of x of t is e to the jt. Right, so this Fourier transform is going to be 2 pi delta omega minus 1. Right, so we can verify that by, let's say if I take a script f here, just say we're doing the inverse Fourier transform of x j omega is 1 over 2 pi. The integral 2 pi delta omega minus 1. Right, so same kind of thing that we've seen over and over again, that we can do our substitution. So in this case, we substitute omega equals 1, and then we're left with the integral of the impulse, which is 1. Okay, so we can see that that does make sense as a result. So what we're going to end up seeing is like your x of t, right? So it's going to look something like this. Right, so you have something that's like an exponential, and then in the frequency domain, you're going to have an impulse at omega equals 1 with a height of 2 pi. So now, if we see what the Fourier transform is of e to the jt, if we want to look at the Fourier transform of x of t is sine 2t. Well, we know that our x of t we can rewrite as a sum of complex exponentials. Right, so we're using the same from that front page of our reference table, right? Converting our sine into exponentials using Euler form. So now, if I want to compute x j omega, so what I can do is I can use the linearity property and say this is just a scale factor. And I want to take the Fourier transform of e to the 2jt. And we have minus 1 over 2j. Our Fourier transform e to the minus 2jt. Okay, so looking at what we had up here with e to the jt, right, we can expand that idea and recognize if we have a 2 up there, right? So the way that we would get back our 2 is if we had an omega minus 2 in there instead. So we have 1 over 2j, 2 pi delta omega minus 2 minus 1 over 2j, 2 pi delta omega plus 2. Combine that together, we get a pi over j delta omega minus 2 minus delta omega plus 2. Right? And so in this case, your x j omega you're going to have at omega is 2 and at omega is minus 2, like so. So it turns out that this idea we can expand for any periodic signal because our periodic signals that can be represented by Fourier series are just linear combinations of these complex exponentials. Right? So we can actually use our Fourier series to get our Fourier transform for periodic signals. Right? Because the idea is that if we can take our x of t and represent this as a sum of these complex exponentials, right, so on and so forth, so we have an infinite number of them, then my xj omega, I have, due to linearity, the scale factor stays the same. And then this complex exponential here, right, we can use the same thing that we observed up here, right? How we can translate these exponentials into deltas. So we have 2 pi delta omega plus 2 omega 0 plus a minus 1, 2 pi delta omega plus omega 0 plus a 0, 2 pi delta omega, right? So on and so forth to however many terms we have in our signal. Or of course we can write this more compactly as x of t, right? We can write in terms of our infinite sum. So our x j omega, right? So we notice that all of these exponentials turned into 2 pi deltas. So we can pull all of the 2 pi's out because they all have that same scale factor. And we're going to have an infinite sum. We're going to maintain those original AKs due to linearity. And our exponentials become deltas in the frequency domain. So if we were to take a look at x of t, we're going to have a periodic pulse train. So it says it's minus 1, 1, 2, so on. Okay. So we've looked at this quite a few times of this form. So our Fourier series, x of t here, we have the infinite summation, ak, e to the j, k. Our frequency is going to be 2 pi over 3 for this case, because our period here, right, 1, 2, 3, right, so t equals 3. We get 2 pi over 3 for our omega. And we can use the formula right from our reference tables. So we can substitute in sine 2 pi over 3k over k pi and 2/3. And so once I have my Fourier series, if I want to compute the Fourier transform, right? So there's one thing to note is that when we do the Fourier series, right, it's still a time domain signal. It's just represented in a slightly different way. The Fourier transform, we're actually converting it to the frequency domain so we can see what is the components basically of each individual frequency. And so we can kind of see that idea in the Fourier series, and that's why it was a good inspiration for us to figure out the Fourier transform. But in this case, right, it's still in the time domain, so we want to convert it to the frequency domain explicitly. So we have x j omega is going to be 2 pi sum ak delta omega minus k omega 0. Right, so kind of the idea, what ends up happening is that it's like you have, as we mentioned before, right, so you kind of have this sinc function, and it's like you're sampling with these deltas, and you get your scale factor from the values of k and this 2 pi out front as well. And so you have another one, say something like here, another one at minus 2 pi over 3, right? So you're at intervals of this omega 0. Right, so we'll take a look at more examples in recitation. So if you have any questions for finishing up the homework, definitely a good chance to do that. But you should have all of the content needed to finish the current homework. If you do have any questions or concerns about any of that, then please let me know. So I did skip over because I wanted to make sure that I did the periodic case because that is part of your homework. But just to kind of go back to those properties, kind of where those two properties that we looked at came from. I have just enough time for that. So proof for the time shifting property. Which says that if we have a time shift, the result of that is we're going to get an exponential scale factor in there. Right? So our x j omega, we know by definition, is the integral of x of t e to the minus j omega t dt. Right, so if I want to figure out the Fourier transform of this time-shifted signal, I'm going to have the integral x of t minus t0 e to the minus j omega t dt. And I can use the same trick that I've used quite a few times and have a change of variables where we let v be t minus t0. So this is the same then as taking the integral x of v e to the minus j omega v plus t0 dv. All right, so once again, we can split up this exponential, take this t0 term outside because it doesn't depend on v, the e to the minus j omega t0, integral, right, looks the same as what we have here. We just have a different dummy variable of integration. So it is indeed this extra exponential term times original Fourier transform. All right, so might look a little odd, but math-wise, turns out that's how we represent shifts. And similarly, the proof for time flip. So we had x of minus t. We're going to get x of minus j omega. Right, so you can get to that the same way by recognizing if you take the Fourier transform of x minus t e to the minus j omega t dt, and we do another change of variables, this time substituting in v is negative t, then what we get is x v e to the j omega v dv. Right, so if we take a look in our original definition, which we have up here, there's a negative sign. In this one, there's not. Right, so it's essentially like we've changed the sign of the omega part here, right? Because the v part, that should stay the same, right? J is just j. So where we're really changing is substituting in a negative omega. That's where those two are coming from, directly from those definitions. All right, so we'll stop there today. And like I said, on Friday, we'll go through some review for the exam. And it'll be nice because you have a little bit of extra time over the weekend to review, see if you have any questions about anything.